In this video, we would like to discuss the components of the earthing system. So our earthing system is consisting of a few components which are really important, and in this next videos we are going to discuss how to design each of them. So starting with the first component, which is the earthing conductor, you will see that here, for example, this is a TT network or TT earthing system. We said that we have here the enclosure of our equipment. Then this enclosure is connected through a conductor, an electrical conductor, and to an earth or to the earth through another component, which is the earthing electrode. Then finally all of this is immersed inside the soil. Okay, so again another picture or another image for this. You will find here this is our earthing cable. Okay, our earthing conductor. It takes the earthing conductor going through an electrode, and this electrode is immersed inside a soil. Okay, so the first component is the earthing conductor. Second component is the earthing electrode, which is this one. Okay, and finally the type of soil, which is our component immersed into, or our electrodes immersed in. And another thing, which is the of course the connection between the conductor and the electrode, which is known as the accessories, termination fittings, bonding, welding kits, and other materials. So these are the main components of the earthing system. We will have to identify the type of soil, then how to design the earthing electrode and what is the material made of, and the earthing conductors. So at first, let's see here, we are talking now about the soil. The soil itself having a specific resistivity or ohm meter. The resistivity of the soil affects the earthing resistance. Okay, so as you remember that from our previous videos, we said that we would like to obtain a 2 to 5 ohm as a resistance, or of course less than this. So in order to produce a very low resistance, so we have to select the electrodes and design the electrodes, the conductors, and all of these components together in order to produce a low resistance. So the soil plays a critical role in the earthing resistance. Okay, you will find that the resistivity of the soil is a factor inside the equations of the resistance of the conductors or the resistance of the electrodes. So we have to identify the resistivity of the soil. So the resistivity of the soil depends on many factors. The first one is the composition of the soil. Is the soil itself is clay or moist, or it is a sandy or a limestone, or etc. Okay, so each type of this soil, the clay, the sand, the limestone, all of this have a different resistivity. So this is the first thing which plays an important role in the resistivity effect. So as an example, you will find that the clay have a lower resistivity than the limestone. The reason for this is that clay or this type of soil, you will find it has a large amount of salt. So as the amount of salts inside the soil itself increases, the resistivity starts to decrease. So as the percentage of the salt content increases, the resistivity of the soil decreases. Okay, so this is the first thing. So one of the components or one of the solutions available for us to decrease the earthing resistance is to put more salts inside the soil. Okay, so this is the first factor. Second factor is the moisture content of the soil. So as the moisture or soil moisture percentage increases, the resistivity of the soil starts to decrease. You will see that here as 10%, 20%, and so on until 100%, you'll find that resistivity decreases or changes from, as an example, from 60,000 to less than 100, for example. Okay, so as the moisture of the soil increases, the resistivity of the soil decreases. Another thing is the temperature of the soil. As the temperature of the soil increases, the resistivity starts to decrease. The depth of the soil. As we go deeper inside the soil, you will find that the resistivity of the soil starts to decrease. So here you will find here at a depth 1 meter, 1.5, 2 meter, 2.5. As the depth increases, you will find that the resistivity starts to decrease. Okay, and you'll find here one curve for the dry soil and one for the wet. You know that the wet, of course, is having a higher percentage of moisture, of course, than the dry. So the wet is having a lower resistivity than the dry. This one is the dry and this one is the wet. So we'll find here the wet at 0.5 depths, 1000, and this one is nearly 2000. Okay, as an example, of course. And another thing which it changes the earthing resistance is the number of electrodes used. As the number of electrodes used increases, then the earthing resistance will start to decrease, because these electrodes are connected in parallel. So as the parallel connection increases, then the soil resistivity starts to decrease, or the total earthing resistance starts to decrease. So the soil resistivity, for example, for the moist soil is a 30 ohm meter, for a clay soil 100 meter, and increasing, you will find that at a dry soil 1000 ohm meter, and at rocky ground you will find that it is a 30,000 resistivity. So the most difficult one is the rocky ground. In this rocky ground is very difficult to produce the grounding system. It is very costly. So how to decrease the soil resistivity in the poor soil? For example, if we have a soil with a high resistivity, so how we can decrease it? So we can do it by using chemical treatment of soil, by adding salts to the soil. Of course, the salts, as you know, that it increases the conductivity of the material. Okay, the salts in water is the reason for conductivity. Okay, so increasing the salts in water increases the conductivity of the water, or here the soil. So we form holes at a distance 10 centimeter from the electrode and at a depth of 30 centimeter, and we start adding these salts. We fill these holes with salts such as the copper sulfate, the magnesium sulfate, or sodium chloride, okay, or NaCl. All of this helps to increase the conductivity of soil, which in the end leads to a lower soil resistivity. And again, the soil resistivity is a really critical and important factor in the resistance of the electrodes and the resistance of the conductor inside the soil.